In this video, we begin section 3.3 on trigonometric substitution. So we are going to be looking at three different types of trigonometric substitution. And what they all have in common is this particular set of forms. The first form is a square root of some constant squared minus x squared, and that's what we're going to be looking at first. The second form is the square root of a constant squared plus x squared. And then the third form, which looks like the first one, but the order is reversed, is we have x squared minus the constant squared, right? These two are not the same. So let's take a look at integrals involving the square root of some constant squared minus x squared. So, as usual, these boxes are not always the easiest things to read, but I'm just going to go over a couple of things here, and then we'll just jump right into doing an example. So the first thing that we want to look at is we have an integral, and we want to see if we see this particular square root. So here's an example, pretty basic one. We have the integral of 1 over the square root of a squared minus x squared. Here's where we have the integral of an x divided by the square root of a squared minus x squared. And here it's not in the denominator. We have the integral of x times the square root of a squared minus x squared. What they all have in common is that particular form. Now, when you see that particular form in an integral, first thing you want to be thinking of is, aha, this is going to be a trigonometric substitution. And so the substitution that we're going to do is going to involve letting x be equal to a, the constant, times the sine of the angle theta. That's the key part right here. And when you see this form, this is going to be your trigonometric substitution. All right, so let's just jump in and do an example. By the way, these are very time-consuming examples. I didn't allocate myself enough space for some of these, so I had to write very small, and I crammed a lot of stuff into a very small space. So hopefully you guys can read this. So here's my original problem. And what I like to first do is identify that this is the form that I'm looking at. So yes, this is the form square root of a squared minus x squared, where a is equal to 3. So the trigonometric substitution says we let x be equal to a sine theta. So a being 3, we end up with the substitution of x being equal to 3 sine of theta. Now the reason this is a substitution is we are now going to substitute this value of x into the square root. So we're going to remove the x, and we are going to put in what x is equal to. That's a substitution. Since x is equal to 3 sine theta, we remove the x, we put in 3 sine of theta. So now the rest of this, all of this is just simplifying. Now, it's easy enough most cases, once you get the hang of it, to do this in your head, knowing what your outcome is going to be. But as you're getting used to doing these, I would strongly suggest, just to make sure that you understand what's going on, that you go through step by step, just like I've done in my notes. So the first thing we do is square 3 sine of theta, and I get 9 sine squared theta. Now, there's a common factor of 9. So in the next step, I factored out the 9, leaving me with 1 minus sine squared theta. 1 minus sine squared theta should look familiar. That is a trigonometric identity, one of the Pythagorean identities that we used in the last section, and it is equal to cosine squared theta. So we have 9 times the cosine of squared theta. Now, if you've done this correctly, a very interesting thing is going to happen here. The constant 9 is a perfect square, and now the cosine squared theta is a perfect square. So what happens is we essentially get rid of the radical. By taking the square root of that, we end up with 3 cosine theta. And that's why we're doing all of this. Well, the purpose of what we're doing is to get rid of that nasty square root. You know from our work with surface area and arc length that trying to integrate something with a square root can be very nasty. All right, the next thing we need to do is find dx. I should have done that up here. I usually do. So if x is equal to 3 sine of theta, then dx is 3 cosine of theta. So that's the first step in this lengthy process. Identify the form. Identify your form, square root of a squared minus x squared. Identify what your substitution is going to be. X is going to be 3 sine of theta. Substitute it in and simplify it. Step 2 is let's do the substitution. Now let's do that in a different color. So we do the substitution over here. Well, this whole radical simplified to 3 cosine of theta now, right? That's what we do with this down here. That whole, the square root of 9 minus x squared became 3 cosine theta. We took the derivative. We had to find dx. The derivative is 3 cosine theta, d theta. I didn't put the d theta there. That goes here. And that's that. Multiplying that together, we get 9 cosine squared theta. All right, bringing the 9 out in front, we are now pretty much done with the first part of the trigonometric substitution part. The next part is what we did in the last section. We have trigonometric integrals that we have to integrate. So remember how to integrate an even power of cosine. We're going to use another one of the identities from trigonometry. This time it's this one. 1/2 plus 1/2 cosine of 2 theta. It's being substituted in for cosine squared theta. And then multiplying, finding the antiderivative of that. The antiderivative of 1/2 is 1/2 theta times 9 is 9/2 theta. The antiderivative of cosine of 2 theta times 1/2 is going to be 1/4 sine of 2 theta times 9 is 9/4 sine of 2 theta. So that's the antiderivative. Now, here's another little trick. We do not want to leave sine of 2 theta as a double angle, right? We could have done that in the last section, but in this section, we can't leave a double angle. It's just going to make our lives very complicated. So how do you get rid of a double angle, sine of 2 theta? Well, there's a trigonometric identity for that. And that is 2 sine theta cosine theta. Sine of 2 theta is equal to 2 sine theta cosine theta. We use a lot of trigonometric identities in this section. So I put that in here for the sine of 2 theta. Now we're reduced to single angles. Multiplying that by 9/4, and we get this. All right, so here comes the next new part. What we want to do now is just like with any substitution. When you first learn how to do substitution in an algebra class, you start with x's, you substitute in u's, like when you do u substitution when we're integrating. Well, then what you have to do at the end is you have to substitute the x's back in. You start with an x, you end up with a u, you have to get back to x's again. Well, we started with x's, we ended up with thetas, with angle measures. We need to get back to the x's again. So how do we do that? Well, we're going to create a triangle. And so that's what this is all about. Let's go to a new color, green. So I create my right triangle. Everything that we're going to be doing now is based on right triangle trigonometry. We're going to go back to how we identified, let me get rid of this, how we identified our original, angle. Okay, we said x is equal to 3 sine of theta. That was our original substitution. All right, so if x is equal to 3 sine of theta, then the sine of theta is equal to x divided by 3, which is what I wrote down here. Just algebraically rearranging that. Why do we want that? We want that because from that, we are going to fill in the right triangle. Remember that the definition of sine in regards to a right triangle is opposite over hypotenuse. So x over 3 is, x is the opposite, 3 is the hypotenuse, and then we can figure out what the other side is by using the Pythagorean theorem. And as it turns out, that third side is always going to be our original, square root. Okay, so now that we have that, we have all of the sides of our right triangle figured out. We need to figure out arc sine of x over 3. All right, so first of all, we have to figure out what theta is. We have theta right here. Okay, well, how do we figure out what theta is? Well, we know that the sine of theta is equal to x over 3. To find, if you know the sine of an angle and you want to find the angle, you use your inverse trigonometric functions. In this case, it would be the arc sine. So the sine of theta is x over 3. Then theta is defined as being the arc sine of x over 3. That's just a basic trigonometric identity that you learned either in trigonometry class or pre-calculus. So that's where this comes from. 9/2 times theta becomes 9/2 times arc sine of x over 3. What else do we need to know? Well, we have 9/2 times the sine of theta. Well, what's the sine of theta? Well, we already know that. That's x over 3. And we need to figure out what the cosine of theta is. Well, the cosine of theta, this is getting messy again. The cosine of theta is the adjacent side over the hypotenuse. Definition, right triangle definitions. Cosine of an angle is the adjacent side divided by the hypotenuse, which would be the square root of 9 minus x squared over 3. And that's where this comes from. And that is our final answer once you clean it up a little bit. All right, so cleaning that up, the 3's and the 9's all cancel out, and so you get this nice simplified answer. All right. So there's a lot going on in a problem like this. And so it takes just a little bit of getting used to. A lot of trig identities, a lot of trigonometry. And that's why they're called, trig substitutions. Problem number 2. Okay. So we have a radical. It is in the form of the square root of a squared minus x squared. And so we're going to let x be equal to a sine of theta. Now, what makes this a little bit more interesting is we've got this 4 here, okay, with the 4 there. So notice how this substitution works. So our basic substitution is going to be in the form of x is equal to a times the sine of theta. And so a, in this particular case, is going to be 1/2. Now, why is that? Well, let's take a look and see how that works. So if we let x be equal to 1/2 sine theta, then the derivative, I'm taking the derivative right now. In the last problem I did it later, but I'm going to do it right now just to get it over with. X is equal to 1/2 sine theta. The derivative of that is 1/2 cosine of theta. All right, so now let's see how the substitution works. That's what we're starting with, 1 minus 4x squared. When we substitute in 1/2 sine of theta, we then have to square that, okay? We're substituting it in just for the x. We have to square it. When we square 1/2 sine theta, we get 1/4 sine squared theta. Now notice what happens with the 4 and the 1/4. They cancel out. And so what we're looking at then is the square root of 1 minus sine squared theta, which is the square root of cosine squared, which is a perfect square, which becomes cosine theta. So that whole thing simplifies once again to cosine theta. So another way of looking at this is if you were to take the 1 minus 4x squared and divide both sides by 4, both of these terms by 4, you would get 1/4 minus x squared. And so now, if you think of this as a squared, what's the square root of that? The square root of that is 1/2. And so that's really where that 1/2 here came from our a. All right, step 2 is to do the substitution. So we do the substitution over here. We have the radical becomes cosine of theta. And up here I had dx was equal to 1/2 cosine of theta. So that goes in here. And now we have to do our trig integral stuff. So the 1/2 comes out, cosine times cosine, wow, what do you know, once again, is cosine squared. I did it a little bit differently this time because I got tired of having that 1/2 plus 1/2 cosine 2 theta. I just factored a 1/2 out of that formula, just put it out here. And now that 1/2 times that 1/2 gives me 1/4, so I'm just left with that. Gets rid of those fractions. All right, now we have to integrate that. So the antiderivative of 1 is theta. The antiderivative of cosine of 2 theta is going to be 1/2 sine of 2 theta. Multiplying everything through by the 1/4, we end up with this. So now we need to get rid of the sine of 2 theta. Once again, we substitute in the trig identity, 2 sine theta cosine theta. And now, let's see, what do we have to do? The only thing I did, I just kind of simplified it a little bit more. Multiplied the 2 times the 1/8, got 1/4. So now we have to go, from here, we have to go and do all of this stuff. Okay? We need to get rid of the thetas. We need to get back into x's. And so the substitution that we did originally is the key to the relationship between the x's and the thetas. The relationship between x and theta is that x is equal to 3 or 1/2 sine of theta. All right, so if x is equal to 1/2 sine of theta, that means sine of theta is equal to 2x over 1, or just 2x. The reason I put it over 1 is we can see that the hypotenuse is going to be 1. So the opposite over the hypotenuse, opposite over the hypotenuse, then the adjacent side using the Pythagorean theorem, 1 squared minus 2x squared is equal to this squared, so that's equal to the square root of 1 minus 2x squared. Okay, if sine of theta is equal to 2x, then using inverse trigonometric functions, we get theta is equal to the arcsine of 2x, and the cosine of theta is simply the square root of 1 minus 4x squared. We have to substitute all of those in there. We need theta, right? We have a theta here, so theta is arcsine of 2 theta. Boom. Sine of theta. Well, we've got sine of theta. It's 2x. So, boom. And now cosine of theta. Well, we just figured that out. Cosine of theta is square root of 1 minus 4x squared. Boom, we've got that. Simplify it. I didn't simplify it, but that 2 and that 4 cancel out there, so you end up with an x over 2 times the square root of 1 minus 4x squared. But no big deal, you can see that, plus c. And so we are done. So once again, make sure that you take some time, go through these problems, try to understand the basic parts. There's really 3 parts to these. The first part is over here, doing the actual substitution, which becomes pretty rote. Second part is the integrating. And then the third part is the substituting back in the x's for the thetas. Problem number 3. Okay, so we see we have a radical square root of 4 minus x squared. And so that is in the form that we want. Square root of a squared minus x squared. Our substitution is going to be x is equal to a sine of theta, where in this case a is equal to 2. So x is equal to 2 sine of theta. Taking the derivative of that, dx is equal to 2 cosine of theta d theta. And now we do the substitution. Take out the x, put in 2 sine of theta. Square all that. Factor out the 4. Convert 1 minus sine squared to cosine squared. And take the square root of the whole thing. And you end up with 2 cosine of theta. Okay? So once again, you see that each time we end up with a cosine of theta here. Okay? Now some people just like to memorize that. Say, okay, well when I have this form, I substitute in a sine theta. What I'm going to end up with is like a cosine theta. But if you get easily confused, or there's no sense in memorizing a lot of stuff when you can just figure it out. I'm the kind of person that I hate to memorize stuff if I can just figure it out. So that's what we're doing here, is we are figuring it out. That way I don't have to memorize stuff. All right, step 2 is do the actual integrating. So my radical in the numerator reduces to 2 cosine of theta divided by x. Well, x, again, is 2 sine of theta. That's how we defined our substitution, so I can put that down there, times dx, which I had over there, 2 cosine of theta d theta. Simplificating all of that. This is a fun one. So we end up with, the 2's cancel out, we bring the other 2 out in front, we end up with a cosine squared divided by sine. So what do I do with this? This is where you've got to kind of think about things. All right, okay. Well, what can I do with a cosine squared? Well, one of the things I can do is helpful with these things is can I get everything in terms of the same trigonometric function? So that's what I'm thinking now. Can I get cosine and sine in terms of the same trigonometric function? Well, yeah, I can. I can easily substitute in 1 minus sine squared theta for the cosine squared, and that's divided by the sine. Now, dividing sine into both terms, I get this. Well, 1 over sine is cosecant. Sine squared divided by sine becomes sine. Well, that's much easier than what we were doing. Now, this is, forgot that. This is another one of those, we know that the integral or the antiderivative of secant is the log of secant minus tangent, right? So the antiderivative of cosecant is going to be the log of the absolute value of cosecant minus cotangent. So this is just a given integral that should be in the list of integrals that you memorize. The antiderivative of sine is cosine, negative. And distributing through the 2, we end up with our antiderivative. But it's all in terms of thetas. We now need to go back and turn it back into x's. So how do we do that? We go to our right triangle. So in our right triangle, I gotta use another color. In our right triangle, let's see, what do I need here? I need a cosecant, I need a cotangent, I need a cosine. Well, I'm starting off with sine. All right, well, I know what sine is, so I can identify the 3 sides of my triangle. From that, I can figure everything else out. So sine, again, is opposite over hypotenuse. Use the Pythagorean theorem to find that side. From that, cosecant is the reciprocal of sine. Okay, so just take the reciprocal of sine, and we get cosecant. Cotangent is reciprocal of tangent, and so tangent, I always remember, is opposite over adjacent. So cotangent, then being the reciprocal, is adjacent over opposite. So it's the adjacent side over the opposite side. So that would give me this. And then the cosine is the adjacent side over the hypotenuse. So we get this. So you need to know your right triangle trigonometric formulas, identities. And these two can be combined a little bit. They both have a common denominator of x. They're all absolute value. And these twos cancel out. And so this is what we end up with in simplified form. All right. Fun stuff. That's probably long enough for this video. Part 2 coming up.